My friends, what I have planned today is we're going to mess around with Desmos a little bit. You don't have to grab a Chromebook yet. But let's talk about a few things. First, actually, let's do this. I'm going to create a new one. New. Save changes. No. All right. So, item 1. This is taking us back to Algebra 1. Finding the equation of a line when given 2 points. I talked about last time that we're going to stick with point slope because point slope is one less step and it's the most accepted. So if I have 2 sets of points, say we have 2 comma -8 and -3 comma 7. Now I wanted to find the equation that works. First thing I'm going to do is I'm going to find the slope. Slope is the change in y over the change in x. The slope is a very powerful tool as you progress in math because the slope shows where things change direction. So if I wanted to find the slope of this line, what I do in Algebra 1 is I say, hey, x1, y1, x2, y2. Plug them in, so I get 7 minus 8, -3 minus 2. So that's 15 on top. On bottom, I get -5. So we find we get a slope of -3. I'm pretty sure you all have seen that before. Agree?
Yeah.
And then we're going to be utilizing point slope. And again, point slope is this. Point slope, if you leave your answers in point slope, there are 2 answers that are correct. And they're based on using it. So if I used these values and the slope, I'm going to get y plus 8 equals -3, x minus 2. So that's the linear equation that goes with it. But if you had used this as your x1, y1, and this, you still get the same slope, you would get this for an answer. Let's see, what am I looking for? x2 plus 3. Both of these answers, my friends, are the exact same linear equation, even though they look different. And how you would decipher that they're the same if you totally solve for y, meaning you distribute it over the parentheses, and got y by itself, they'd wind up being the same thing. But if you keep it in point slope, you're fine. And the nice thing is Desmos allows you to plug something in as point slope. Okay? So that's the first thing I want to hit upon. Second thing is, can I move off here? Let's talk about key points on a graph. Okay, so let's say we have some xy axis, and I'm just going to draw something like this. Okay, I don't know what this equation is. I just know it curves a bit. So I have an absolute max in the y direction, which is, in this case, infinity, because this arrow is going to go to infinity. I have an absolute min in this case is going to be negative infinity, because this is our end behavior is going down to infinity in the y direction. Okay, so that's kind of first thing. But then they get into something saying, what is our relative max and what is our relative min? And our relative max and min are turning points of our graph, meaning it goes from where it goes going up to going down. The top of a roller coaster for a relative max. Relative min is when you're at the bottom of the hill and you start going up the other side. So let's label the relative max. So this would be a point x comma y. So the y value is what you do. You also have a relative max here. And again, that's a point x comma y in which we're going to look at the y value. And then these down here are called relative mins. So you have an x and a y in which you focus on the y value. And right here, again, that's an x comma y, and you look at the y value. Okay? So those are a couple of key points that exist on a graph. Realizing what's our end behavior going? Where's it going in the y direction? Does it go all the way to the right? Where's it going in the y direction? Does it go all the way to the left? And then other key points. All of these are called solutions. The solution is where it crosses the x-axis. X-axis. So this is some 0 comma or some not I don't want to use 0. I'm going to call a number comma 0, a number comma 0, a number comma 0, number comma 0, number comma 0. Does my verbiage make sense so far? Mm-hmm. So those are solutions. That means if I were to plug those x values into my graph or to my equation result would come out to be 0. And then the last key point on a graph is where it crosses the y-axis. And that is 0 comma some number. So those are kind of everything I could talk about with a graph. Okay? Anytime you get to a relative max or a relative min, relative max or min, so the top part or the bottom part, or changes from going up to down or down to up, the slope at that exact spot, can I move off here? Yeah. So you know you have a relative max or min if the slope at that point, so m, is equal to 0. Okay? A line that has a slope of 0 is a horizontal line. Is that okay so far? So what we're going to kind of start working with and start thinking about what's happening with some of these things is this. Let's say we had something like this. What I'm going to do with this is I'm going to take a whole bunch of, that's fine, I like that pink. I'm going to stick with that pink. Let's take a bunch of lines. Hey!
You know what happened in our Jen Ford is you?
Do what?
Jen Ford, because I know she was in the hall.
No idea.
Thank you.
Yeah. So I take a whole bunch of these lines. Each of these lines has a linear equation it corresponds to. One of these lines has a slope of 0, which would be this one. It's the one that's a horizontal line. Those pink lines are called tangent lines. Now, this is not referring to the tangent when you're talking about trig. We're talking about geometry tangent, where it's a line that touches a shape once. Does that make sense? So that's what's taking place with this. So a lot of times, do you all feel comfortable that each one of these pink lines, the slope is a little bit different at each one? because it's changing direction, right? It starts like this, or maybe starts like this, or does this. As it gets to this, as you get to a horizontal line, once you know the slope there is 0, that means you've either gotten to a relative max or a relative min. Now you can do the same idea to this point. Let's find some more. Let's do a custom color. Yeah, baby. Ooh, no. I want to find a color that I like. And we'll go with that one. Okay. So let's do this. I'm going to do the same thing here. Okay, so each of these tangent lines, meaning a line that touches the shape once, each of those lines has a slope that goes with it. And once you find the slope that is 0, that means you've gotten to either to a relative max or a relative min. Does that kind of vocabulary make sense? Try. So this is kind of good because there's times it could give you a word problem that might say the slope at this point is 0. And as soon as you hear them say the slope at a point is 0, that means it's either a max or a min, relative max or min. You're not all too worried about the absolute max or min unless it's saying, hey, what's the end behavior of this graph doing? So those are just a couple of terminologies that we're going to talk about. There's another term that I want to talk about. It's called an asymptote. Now, you can have vertical asymptotes. You can have horizontal. And there's a last one is called slant, but it's also called end behavior asymptote. Okay? The vertical asymptotes take place when your denominator equals 0. Your horizontal asymptotes take place in two different scenarios. If the degree, which is the exponent, on top is less than the degree on bottom, you get y equals 0 is your horizontal. So what I mean is if I had like x to the third over x to the fifth, the degree on top is 3, the degree on bottom is 5. So this would have a asymptote of y equals 0, a horizontal asymptote. If the degree on top and bottom are equal, it's y equals a over b. Now I go, I don't know what that means. Okay, well, I'll show you. So let's say I have y equals 7x to the fifth over 10x to the fifth. The degree on top and bottom are the same. So you take your, whatever the leading coefficient is to your highest exponent, and you say, well, that would mean that y equals 7 over 10. Okay, so that's a horizontal line that's up 7/10 between 0 and 1. Almost, closer to 1 than it is to 0. These are horizontal asymptotes. If the degree on top is greater than degree on bottom, so if you had like x to the 7th over x to the 3rd, degree on top is bigger than degree on bottom, you have something called an end behavior asymptote. You don't have a horizontal asymptote. Okay, so that's just to give you some idea. Now, I know we talked about yesterday a little bit of a graph, and I'm going to draw one up that kind of looks similar to what maybe we talked about yesterday. Can I move off here?
Yeah.
Okay. So let's say I have my XY axis. These are asymptotes. So I have this, this, and this. So this is x equals a number as an asymptote. This is x equals a number as an asymptote. That would be where the denominator, those are where the numbers where the denominator would be equal to 0. And this would be y equals a number. So this one, because it's off the x-axis, would mean I have the same degree on top as I have on bottom, which means I have a horizontal asymptote. These do not have an end behavior asymptote because the degree on top is equal to the degree on bottom. The only time you have an end behavior or a slant asymptote is when the degree on top is greater than the degree on bottom. So I'm going to give you a sheet. Oh, one last thing I need to go over. Actually, we can do these. Let's have you do the first 4 problems on here. And you're allowed to use one of my graphic calculators. You're allowed to use Desmos on your phone. You're allowed to grab one of the Chromebooks and use Desmos on that. Let's see if you can do the first 4 problems on this. The 4th one's going to be a little trickier.
Oh, I thought there was only one question.
What's that?
You got food? I thought there was only one question on the quiz.
Oh, it's not a quiz. Oh, this is just notes like practicing what I talk. First 4. Just try the first 4. What? Yeah.
You like Phoenix, Arizona?
Hey, grew up there.
Did you like it?
That's fine. That's a swimming pool.
What part of
Actually, Tempe.
Okay. I might go out there.
Tempe is southeast of Phoenix.
That's where ASU was.
ASU. I grew up about a mile and a half from Arizona State.
Yeah, you was sneaking into them parties. You was walking there in front of I already know.
All right, so first one, they just want us to find the linear equation. So x1, y1, x2, y2. Slope is y2 minus y1 over x2 minus x1. So I get 3 minus 6 over negative 4 minus 2 equals negative 3 over negative 6. So I get a slope of 1/2. Yes?
Yeah.
Giddy up. Find the equation. I'd keep it as point slope. So y minus y1 equals m times x minus x1. If you use this as x1, y1, you get y minus 6 is equal to 1/2 x minus 2. If you use this one as your x1, y1, you're going to get y minus 3 equals 1/2 x minus 4, so x plus 4. So both of these answers are correct. You only have to list one of them. Seem legit? Problem number 2. They would like us to sketch the graph of the following functions, label all key points, intercepts, max, min, asymptotes, etc. So problem number 1, or this problem here, doesn't have any asymptotes. Because I'm not dividing, I don't have a fraction where I have a denominator with an x in it, there's not going to be an asymptote. Being I don't have any weird things taking place, this is just a 3rd degree polynomial, which kind of looks like this. And behavior's doing this, where a bunch of wiggle takes place right here. So let me just plug that into my own Desmos and see what we can say. Yes, and let's come. Grab the calculator. Y equals x to the 3rd minus 2x squared minus 6x minus 5. All right, so some key points we have here. I'll zoom out a little bit. Looks like I can see everything I need. I go to projector mode, so it's a boulder. So some key points. This is a key point. Okay? That's a 0. Agree? This is a relative min. So you have a relative min. In the y direction happens at negative 17.236. We have our cross of the y-axis at 0, 5. We have a relative max in the y direction that happens at 1.949. And that's all we have to list about that graph. Okay? We labeled the x-intercept. There was only one in this case. We labeled the max and mins. We labeled the x-bar across the y-axis. And this one, again, had no asymptotes. Good enough? May I go back to the smartboard? Okay, so this next problem, this will indeed have both an x, have a vertical and a horizontal asymptote. First thing I'm going to look at, the degree on top and the degree on bottom. This is x to the first, this is x to the first. They're equal. So I have a horizontal asymptote, we'll call it ha, at 3 over 1. So y equals 3 over 1. Y equals 3 over 1 is just 3. Okay? So that we have a horizontal asymptote there. We have a vertical asymptote at where that's equal to 0. So we have a vertical asymptote at 2. We have a horizontal asymptote at 3. Okay, so let's take a look at what that looks like on Desmos so we can verify and know what we're seeing. Clear that. Let's go with y equals 3x divided by x minus 2. All right, so help me out. Where did I say my vertical asymptote was? What did I say it was?
3.
Was that?
1, 2.
So I have y equals 3 and x equals 2. Y equals 3 and x equals 2. Y equals 3, x equals 2. You see how those two asymptotes took place up there?
Yes.
That's all it's dealing with the problem. Okay? What are some key factors? I'm going to get rid of these two equations because I know they're there. So I have this. That happens to be where it crosses the y-axis. It also happens to be a solution because it crosses the x-axis right there as well. There's no other key features to this graph. You could zoom out all day long, and this graph is just going to, I'm not at the 100,000 now. So that's what this graph's doing. So again, you're just kind of worried about what's taking place there. And then problem number 4, it says they want you to use the math menu, but you don't have to use that. Don't do that. Just go on Desmos. So let's know what this means. I'm looking, where is graph below the x-axis? Okay, so I'm going to cheat for a second. I'm going to use Desmos because there's no y equals on this, but I'm going to say y equals just to take a look at the graph. I want it below the x-axis. So I'm just going to go y equals x squared minus 2x minus 15. Zoom out a smidge. So between here and here, those are my solutions. Here, hey, that's called a vertex, but it's also a minimum. Okay, and it's not a relative min because my absolute maximum is infinity, and I don't have an absolute minimum. My absolute minimum has got to be negative 16. So what we're worried about is this region here, the region below the x-axis. Being that our original has the equal sign, we're going to use square brackets on it. So negative 3 and 5. So where would this exist? Between negative 3 and 5. Hard brackets on both. because of the equal sign. This is where our graph gives a negative y value and also the 0. And when I say also the 0, that's because I have the equal sign there. That's what that takes place with. So I haven't really talked about domain too much, but would you do the best you can? So first part of next class, see if you can figure out 5, 6, and 7, or soon. 5, 6, and 6. There's 2 6s because, we can't count in here. There's nothing on the back. So you just 3 problems to try. We'll go over those first thing next time we have class. Sound like a deal?
Yes.
Yeah, baby.